let yourself sink deeper into comfort. Feel the weight of your body pressing gently into the surface beneath you, as if you're being cradled by the very fabric of existence itself. Take a slow breath in, drawing air deep into your lungs, and as you exhale, allow any lingering tension to dissolve like morning mist under the first rays of sunlight. Tonight, we're embarking on a journey that will stretch your imagination across distances so vast they dwarf even our wildest dreams. But there's no effort required on your part. Simply close your eyes if you haven't already, or let your gaze rest softly on some distant point, and allow the story to wash over you like gentle waves lapping at a peaceful shore. We're going to explore something remarkable, something that changes everything we thought we knew about the size and scale of reality itself. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, has just revealed truths about our universe that leave even seasoned astronomers stunned and speechless. But don't worry about remembering every detail or grasping every number. Let the words paint pictures in your mind. Let them carry you across cosmic distances, and trust that the wonder will settle into your thoughts like snowflakes finding their resting place. And before we drift into the depths of space together, I want to take just a moment to say this. If you're finding comfort in these journeys we take together, if these stories help you unwind or carry you gently toward sleep, consider subscribing to The Science Pillow. By subscribing, you're helping this channel grow and ensuring that more of these calming cosmic journeys can find their way to you. And if you're feeling particularly generous with your appreciation, a like on this video helps others discover this peaceful corner of the internet, this place where science and serenity intertwine. Your support means the world, truly, and it allows us to keep exploring the wonders of the cosmos, together, one soothing story at a time. Thank you for being here, for sharing this moment, for opening your mind to the magnificent mysteries that surround us. Now, let's begin our journey. Breathe deeply, relax completely, and prepare to discover just how vast, how incomprehensibly large, our universe truly is. Us, the power of Webb, a new eye on the cosmos. On Christmas morning in the year 2021, while families across much of the world were unwrapping presents and gathering around tables laden with holiday feasts, something extraordinary was happening in the darkness before dawn along the northeastern coast of South America. In French Guiana, at Europe's spaceport, a rocket stood poised against the pre-dawn sky, its sleek form illuminated by floodlights that painted it in stark relief against the tropical darkness. Inside that rocket, folded like the most intricate origami you could imagine, was an observatory that had taken 3 decades to design, countless billions of dollars to build, and the collective efforts of thousands of the brightest minds in science and engineering to bring to reality. The James Webb Space Telescope. Even the name carries weight, honoring James E. Webb, who led NASA during the pivotal years of the Apollo program, though many have questioned whether the telescope's name should honor others who contributed more directly to its creation. But names aside, what matters is what this machine represents, humanity's most ambitious attempt yet to peer into the deepest recesses of space and time, to see the universe as it was when it was young, to understand the very origins of everything we know. When the Ariane 5 rocket's engines ignited, they unleashed a controlled explosion of such tremendous power that the ground shook for miles around. The rocket lifted off, rising slowly at first, then faster and faster, carving a luminous arc across the dark sky as it fought against Earth's gravity to carry its precious cargo into space. For those who had spent years, sometimes entire careers, working on this telescope, the launch was a moment of almost unbearable tension. They knew that everything could still go wrong. Space is unforgiving, and this telescope was unlike anything that had ever been launched before. Consider the engineering challenge for a moment. The James Webb Space Telescope has a primary mirror that measures 6.5 meters across, significantly larger than the Hubble Space Telescope's mirror of 2.4 meters. But there's a problem. No rocket fairing, the protective nose cone that shields payloads during launch, could accommodate a mirror that large in one piece. The solution was to build the mirror in 18 separate hexagonal segments, each one capable of being precisely positioned to work together as a single, perfect mirror. These segments would have to unfold in space, a terrifying prospect when you consider that there would be no way to send astronauts to fix any problems, unlike with Hubble, which orbits low enough that the space shuttle could reach it for repairs. But the mirror was just the beginning of the folding challenge. Webb also carries a sun shield the size of a tennis court, a massive 5-layer structure designed to protect the telescope's sensitive instruments from the heat of the Sun, Earth, and Moon. This sun shield had to be folded down to fit inside the rocket, then carefully deployed in space through a sequence of steps so complex, so precisely choreographed, that engineers described it as unfolding like a transformer. Each layer of the sun shield is thinner than a human hair, made of a material called capton, and each one had to separate and tension perfectly, or the entire mission would fail. For 29 days after launch, as Webb traveled to its destination, engineers and scientists watched anxiously as the telescope began its unfolding sequence. One by one, hundreds of mechanisms had to work perfectly. The sun shield unfolded, the mirror segments deployed, secondary structures locked into place. With each successful step, those who had devoted their careers to this project breathed a little easier, though the tension wouldn't fully lift until every system was tested and verified. Webb wasn't heading into orbit around Earth like most satellites. Its destination was a special place in space called the second Lagrange point, or L2, located approximately 1.5 million kilometers from Earth in the direction opposite the Sun. Now, you might wonder what makes this location special. Lagrange points are positions in space where the gravitational pull of two large objects, in this case the Sun and Earth, combined with the orbital motion of a spacecraft, create a stable configuration. At L2, Webb can maintain a position where the Sun, Earth, and Moon are always in the same direction, meaning the sun shield can constantly protect the telescope's cold side from their heat. This is crucial because Webb observes in infrared light, which is essentially heat radiation. For the telescope to detect the faint infrared glow of distant ancient galaxies, its instruments must be kept extraordinarily cold, around negative 223 degrees Celsius, just 50 degrees above absolute zero. Any heat from the telescope itself would overwhelm the faint signals from the early universe, like trying to see the glow of a candle while standing next to a bonfire. The sun shield blocks more than 1 million times the amount of heat that reaches the cold side, providing sun protection equivalent to SPF 1 million. The infrared capability is what makes Webb so revolutionary. The Hubble Space Telescope, which has served humanity brilliantly for more than 3 decades, observes primarily in visible light with some ultraviolet and near-infrared capability. but the universe's expansion stretches light from the most distant objects, shifting it from visible and ultraviolet wavelengths into the infrared. This phenomenon, called redshift, means that the earliest galaxies, formed when the universe was just a few 100 million years old, are essentially invisible to telescopes that can't see deeply into the infrared spectrum. Think of it this way. When you hear an ambulance approaching, its siren sounds higher in pitch. As it passes and moves away from you, the pitch drops. This is the Doppler effect, caused by the compression of sound waves as the ambulance approaches and their stretching as it recedes. Light works similarly. Objects moving toward us have their light shifted to shorter, bluer wavelengths. Objects moving away from us have their light shifted to longer, redder wavelengths. And because the universe is expanding, with distant galaxies racing away from us, their light arrives stretched, reddened, shifted into the infrared. Webb's instruments are specifically designed to capture this infrared light. The telescope carries 4 main instruments, each one a masterpiece of engineering. There's NIR-CAM, the near-infrared camera, which serves as Webb's primary imager and can detect light with wavelengths from 0.6 of a micrometer to 5 micrometers. NIR-CAM was also crucial during the telescope's alignment phase, serving as the wavefront sensor that allowed engineers to precisely position each of the 18 mirror segments. Then there's NIR-SPEC, the near-infrared spectrograph, capable of observing 100 objects simultaneously through its innovative microshutter array. This allows astronomers to collect spectra from multiple galaxies at once, dramatically improving efficiency. Spectra are like fingerprints for astronomical objects, revealing their composition, temperature, motion, and distance by showing how light is distributed across different wavelengths. The third instrument is MIRI, the mid-infrared instrument, which can detect longer infrared wavelengths from 5 to 28.5 micrometers. MIRI had to be cooled to an even lower temperature than the rest of the telescope, just 7 degrees above absolute zero, requiring its own dedicated cooling system. This extreme cold allows MIRI to detect the warm glow of dust and the heat signatures of distant galaxies. Finally, there's the fine guidance sensor and near-infrared imager and slitless spectrograph, mercifully shortened to FGS/N-IRISS. This Canadian-built instrument helps keep Webb pointed precisely at its targets while also conducting its own scientific observations, particularly in the hunt for exoplanets and their atmospheres. All of these instruments work together, fed by light gathered by that magnificent golden mirror, which is coated with a microscopically thin layer of gold to optimize its reflectivity in the infrared. The mirror's 18 segments must work in perfect harmony, their positions adjustable with nanometer precision through small actuators on the back of each segment. This allows the telescope to maintain its optical perfection even as it experiences the temperature fluctuations of space. The result of all this engineering, all this innovation, is a telescope that can detect objects 100 times fainter than Hubble can see. Webb can peer back to approximately 100 to 250 million years after the Big Bang, potentially glimpsing some of the very first galaxies to form. For comparison, Hubble could see back to about 400 million years after the Big Bang, to a galaxy called GN-Z11. Webb shattered that record within months of beginning science operations. When the first images from Webb were released on July 12, 2022, the world watched in awe. Even those first glimpses exceeded expectations. President Joe Biden revealed the first image the day before, on July 11th, at a White House event. It showed a galaxy cluster designated SMACS 0723, a portrait of the universe as it appeared 4 6/10 billion years ago. The image, which took 12.5 hours to capture, revealed thousands of galaxies in a patch of sky approximately the size of a grain of sand held at arm's length. But that was just the beginning. In the months and years that have followed, Webb has been peeling back layer after layer of cosmic mystery, revealing a universe far stranger, far more wondrous, and far larger than we had imagined. The telescope has shown us stars being born in clouds of gas and dust, planets forming around distant suns, galaxies colliding and merging across billions of light years. It has detected the chemical signatures of water and other molecules in the atmospheres of planets orbiting other stars, bringing us closer to answering that most profound question: are we alone? But perhaps Webb's most stunning revelation concerns the sheer scale of the universe itself, the incomprehensible vastness that surrounds us. This discovery didn't come from a single image or observation. Rather, it emerged from the collective weight of thousands of observations, from galaxies detected at the edge of time, from measurements of cosmic expansion, from maps of dark matter that show how the universe is structured on the grandest scales. Webb has revealed that the universe is not just large in the way we previously understood. It's larger, more complex, more intricate than our theories predicted, stretching our understanding to its limits and beyond. Rewriting the observable universe. Let's start with a question that seems simple but opens doors to mind-bending concepts. How big is the universe? Take a moment to consider this. You might be tempted to answer with a number, perhaps 13.8 billion light-years, which is the age of the universe measured from the Big Bang until now. If the universe is 13.8 billion years old, and light travels at a finite speed, then surely we can see 13.8 billion light-years in any direction, making the observable universe 27.6 billion light-years across. Right? It's a reasonable thought, but it's wrong. And understanding why it's wrong will help us grasp one of the most profound truths about the cosmos. Space itself is expanding, and it's been expanding all along. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is approximately 93 billion light-years in diameter. Let that number settle for a moment. 93 billion light-years from one edge to the other, with Earth sitting somewhere near the center of our observable sphere. But how can this be if the universe is only 13.8 billion years old? How can we see light from places that are farther away than light could have traveled in the age of the universe? The answer lies in understanding that the universe isn't static. It's not a fixed stage on which cosmic events play out. The universe itself, the fabric of space, is stretching, carrying galaxies along with it like raisins in a rising loaf of bread. When we look at distant galaxies, we're seeing them as they were billions of years ago, when they emitted the light that's only now reaching our telescopes. But in the time that light has been traveling toward us, the universe has been expanding, and those galaxies have been carried even farther away by that expansion. Consider a galaxy whose light was emitted 13.8 billion years ago, right at the edge of the observable universe. When that light began its journey, the galaxy might have been much closer to where Earth would eventually form, perhaps just a few 100 million light-years away in the very young, very compact universe. But as the light traveled through space, space itself was stretching, lengthening the distance the light had to cross. Meanwhile, the expansion was also carrying that distant galaxy away from us at tremendous speed. By the time the light finally reaches us, having traveled for nearly the entire age of the universe, the galaxy that emitted it is now approximately 46.5 billion light-years away. This is the comoving distance, the distance measured accounting for the expansion of space that has occurred during the light's journey. In every direction we look, we can potentially see light from objects now located about 46.5 billion light-years away, giving us that total observable universe, diameter of approximately 93 billion light-years. Now, here's where Webb comes into this cosmic story in a way that transforms our understanding. Before Webb, we knew that the observable universe was approximately this size, but we could only glimpse the most distant regions in a limited way. The Hubble Space Telescope could peer back to about 400 million years after the Big Bang, detecting faint, small, distant galaxies at the very edge of its capabilities. These observations were precious, hard-won victories against the limits of technology, and they taught us much about how galaxies form and evolve. But Webb changed everything. With its enormous mirror and its exquisite sensitivity to infrared light, Webb can see not just a little farther than Hubble, but dramatically farther, and with far greater clarity. When Webb pointed at regions of space that appeared nearly empty to Hubble, it revealed that these regions were actually teeming with galaxies, thousands upon thousands of them, stretching back to the earliest epochs of cosmic history. The first deep field image, that picture of galaxy cluster SMA CS0723, demonstrated this immediately. In that tiny patch of sky, no bigger than a grain of sand at arm's length, Webb detected thousands of galaxies. Some of these galaxies existed when the universe was less than 1 billion years old, their light traveling for more than 12 billion years to reach our telescopes. The image showed not just the distant galaxies, but also the complex structure of the universe on cosmic scales, with massive galaxy clusters in the foreground, using their gravitational fields to lens and magnify even more distant galaxies behind them. This technique, gravitational lensing, is predicted by Einstein's general theory of relativity. Mass warps the fabric of space-time, and light follows the curves in space-time. When light from a distant galaxy passes through the warped space-time around a massive object like a galaxy cluster, its path bends just as light bends when passing through a glass lens. If the alignment is right, the foreground mass can act like a cosmic telescope, magnifying the background galaxy and making it appear brighter and larger than it would otherwise. Webb has used gravitational lensing to peer even deeper into the universe than its already extraordinary capabilities would normally allow. Some of the most distant galaxies Webb has detected appear in these lensed images, their light stretched and distorted into arcs and multiple images by the gravitational influence of foreground clusters. These lensed galaxies provide windows into the universe as it existed just a few 100 million years after the Big Bang, when the very first galaxies were forming. But Webb didn't stop with that first deep field. The telescope has conducted multiple deep field observations, including a return to one of the most famous regions of sky ever photographed, the Hubble Ultra Deep Field. This tiny patch of sky in the constellation Fornax had been observed by Hubble for hundreds of hours, revealing nearly 10,000 galaxies, some of them among the most distant known at the time. When Webb turned its gaze to this same region, it revealed a universe that Hubble could only hint at. The MIRI Deep Imaging Survey, one of Webb's longest observations of an extragalactic field, spent nearly 100 hours observing the Hubble Ultra Deep Field region with the mid-infrared instrument. The resulting image revealed more than 2,500 sources, many of them extremely red galaxies likely dating from the early universe. These red objects could be massive galaxies obscured by dust, or they could be very distant galaxies with mature stellar populations formed surprisingly early in cosmic history. Webb's infrared vision allows it to see through cosmic dust that would obscure these galaxies in visible light. Dust grains, composed of elements like carbon and silicon, that formed in the cores of ancient stars, scatter and absorb visible and ultraviolet light, but allow infrared light to pass through relatively unhindered. This makes Webb particularly adept at finding galaxies that are both very distant and very dusty, objects that might be almost invisible to optical telescopes but shine brightly in the infrared. The statistics are staggering. In survey after survey, Webb has detected hundreds of thousands of galaxies. One survey, called Cosmos Webb, detected approximately 800,000 galaxies in its observations, creating detailed maps showing how galaxies cluster together across cosmic history. These observations revealed 1,678 galaxy groups, some of them among the most distant ever detected, helping astronomers understand how galaxies come together under gravity's influence to form the large-scale structure of the universe. Each of these galaxies is a system of billions, or even hundreds of billions of stars, many of them likely hosting their own planets. Each galaxy formed through the gravitational collapse of gas in the early universe, grew through the merger of smaller galaxies, and evolved through billions of years of star formation. And Webb can see thousands upon thousands of them in single images, each one a distant island of light in the cosmic ocean. The scale becomes even more impressive when you consider what each of those faint smudges of light represents in terms of distance. A galaxy appearing in one of Webb's deep fields might be 10 billion light-years away, meaning we're seeing it as it existed 10 billion years ago, when the universe was less than a quarter of its current age. The light from that galaxy, carrying information about its stars and gas and the supermassive black hole likely lurking at its center, has been traveling through space for 10 billion years, crossing a distance so vast that even moving at the cosmic speed limit, the speed of light, it took 2/3 of the universe's entire history to reach us, and that's not even the most distant galaxies Webb has found. The telescope has detected galaxies at redshifts of 13, 14, and beyond. Galaxies whose light was emitted when the universe was just 280 million to 400 million years old. These are among the earliest galaxies ever observed, formed during what astronomers call the cosmic dawn, the epoch when the first stars ignited and the first galaxies assembled from the primordial gas that filled the young universe. The light from these ultra-distant galaxies has been traveling for more than 13 billion years, across a distance that's now, accounting for cosmic expansion, approximately 30 billion light-years or more. We're not just looking across space when we observe these objects. We're looking back through time, watching the universe as it was in its infancy, seeing events that occurred before our sun existed, before our galaxy had reached its current form, before Earth and everything we know had come into being. This is the true scale of the observable universe that Webb has revealed. Not just 93 billion light-years of empty space, but 93 billion light-years packed with hundreds of billions of galaxies, each galaxy containing hundreds of billions of stars, stretching back through time nearly to the moment of creation itself. And every one of those galaxies, every one of those stars, exists within a universe whose full extent we cannot even guess at, because the observable universe is just the part from which light has had time to reach us. Beyond that horizon, beyond the edge of the observable, the universe continues, perhaps infinitely, filled with galaxies we will never see, stars that will never share their light with us, because the expansion of space itself prevents their light from ever making the journey. Webb hasn't just shown us how big the observable universe is. It's shown us that this vast sphere of 93 billion light-years is alive with structure, with history, with complexity beyond our previous imaginings. The universe isn't empty darkness punctuated by occasional points of light. It's a rich environment of galaxies woven into cosmic webs, connected by filaments of dark matter, evolving through collisions and mergers, forming stars at rates that have varied dramatically across cosmic time. And we're still just scratching the surface of what Webb will reveal. The telescope has decades of operation ahead of it potentially, and with each observation, we're adding to our map of the observable universe, filling in details, pushing back the frontier of the known, discovering new puzzles and new wonders. The true scale of the universe, as revealed by James Webb, is not just a number of light years. It's the realization that we live in a cosmos of staggering richness and complexity, where looking outward means looking backward through time, where the most distant objects we can see are also the oldest, carrying messages from an epoch when the universe was young, and the first light was just beginning to push back the cosmic darkness. The earliest galaxies, cosmic dawn revealed. There's something profoundly moving about seeing light that began its journey when the universe itself was an infant. When Webb detects a galaxy from 13 billion years ago, we're not looking at ancient history by human standards. We're witnessing events from an era when cosmic history itself was just beginning to unfold, when the first generation of structures was taking shape in a universe still almost unrecognizably different from the one we inhabit today. Before Webb, our knowledge of the earliest galaxies was limited and frustrating. The Hubble Space Telescope had pushed back to about 400 million years after the Big Bang, finding a galaxy called GN-Z11 that held the distance record for years. This galaxy, appearing as a small red dot in Hubble's images, represented a triumph of observational astronomy. But it was also clearly just the tip of the iceberg, a single example of what must be a vast population of early galaxies, hiding just beyond Hubble's reach. Webb was designed specifically to break through this barrier, to peer into the era known as cosmic dawn, when the first stars ignited and the first galaxies assembled. And within months of beginning science operations, Webb began rewriting the record books with a series of discoveries that left astronomers both excited and deeply puzzled. In early 2025, astronomers announced that Webb had detected a galaxy designated MOM-Z14, observed as it appeared just 280 million years after the Big Bang. Let that timeline sink in for a moment. The universe is 13.8 billion years old now. This galaxy existed when the universe was 280 million years old, which means we're seeing it as it was roughly 2% of the way through cosmic history. If the universe's entire history were compressed into a single day, we'd be looking at this galaxy as it appeared about 28 minutes after midnight. But MOM-Z14 isn't just notable for its distance. It's what the galaxy looks like that has astronomers scratching their heads in confusion and wonder. According to the observations, MOM-Z14 is brighter, more compact, and more chemically enriched than galaxies at that epoch should be based on our theoretical models. The galaxy shows elevated levels of nitrogen in its spectrum, suggesting that it has already experienced multiple generations of star formation and stellar evolution. Here's why this is puzzling. When the first stars formed, they would have been composed almost entirely of hydrogen and helium, the two elements created in the Big Bang. These primordial stars, called population 3 stars, would have been massive and short-lived, exploding as supernovae after just a few million years. Those explosions would have seeded the surrounding gas with heavier elements, what astronomers call metals, even though this includes elements like carbon, nitrogen, and oxygen that chemists wouldn't classify as metals. Then a second generation of stars could form from gas enriched with these metals, living longer and eventually contributing their own elements to the cosmic mix. This process takes time. For a galaxy to show significant metal enrichment, it needs to have gone through at least one, probably multiple, cycles of star formation and stellar death. That MOM-Z14 shows these signatures when the universe was only 280 million years old suggests that galaxy formation and stellar evolution proceeded much faster than our models predicted. It's as if we expected to see infants and instead found precocious teenagers, already sophisticated and complex. And MOM-Z14 isn't alone. Webb has detected a growing population of surprisingly luminous galaxies in the early universe, objects that appear much brighter than theoretical predictions suggested they should be. One study identified about 300 unusually bright cosmic objects that may be some of the earliest galaxies ever formed, all of them challenging our understanding of how quickly galaxies could assemble and grow in the young universe. The sheer number of these bright early galaxies is part of the puzzle. Before Webb, theoretical models predicted how many galaxies of various brightness levels should exist at different epochs in cosmic history. These models were based on our understanding of how dark matter collapses under gravity to form halos, how gas falls into those halos and cools to form stars, and how feedback from supernova and accreting black holes regulates the star formation process. The models predicted relatively few very bright galaxies in the first few 100 million years after the Big Bang, with the population of bright galaxies gradually building up over time as smaller galaxies merged and grew. Webb's observations show about 100 times more bright galaxies at these early epochs than the models predicted. It's not just a small discrepancy that could be explained by fine-tuning some parameters. It's a chasm between theory and observation, suggesting that something fundamental about our understanding of early galaxy formation may be incomplete or incorrect. Several potential explanations have been proposed. One possibility is that the early universe was simply more efficient at forming stars than we thought. Perhaps the gas in these early galaxies could cool and condense into stars more readily than our models assumed, leading to more vigorous star formation. Another possibility involves the role of supermassive black holes. Webb has found evidence of actively growing black holes in some of these early galaxies, black holes with masses millions or even billions of times the Sun's mass. If these black holes grew rapidly in the early universe, their energy output could affect the appearance of their host galaxies in complex ways. A particularly intriguing class of objects that Webb has discovered are the so-called little red dots. These are extremely compact, very red sources that appear in deep images of the early universe. Their nature is hotly debated. They could be extremely dusty galaxies, where vigorous star formation is hidden behind thick clouds of dust. They could be galaxies dominated by supermassive black holes, where the light we're seeing comes primarily from gas falling into the black hole rather than from stars. Or they might be something we haven't even imagined yet, a class of object that only existed in the early universe and has no modern counterpart. The chemical signatures that Webb detects in these early galaxies add another layer of mystery. Some show evidence of nitrogen enrichment, as in MOM-Z14. Others show unusual ratios of elements that don't match what we'd expect from normal stellar evolution. These chemical oddities could be telling us something profound about the first stars, about how they differed from modern stars, about how they exploded and what elements they produced. Webb has also revealed that the early universe was more diverse than we expected. Galaxies from this epoch come in a remarkable variety of shapes and properties. Some appear as small, compact blobs of light. Others are already showing signs of structure, with multiple clumps that might be individual star-forming regions or even separate small galaxies in the process of merging. A few show extended structures that might be the precursors to the spiral arms we see in mature galaxies like the Milky Way. This diversity challenges the notion that the early universe was a simpler, more uniform place. If anything, Webb's observations suggest that even in the first few 100 million years after the Big Bang, galaxy formation was a rich and complex process, with different galaxies following different evolutionary paths. Some assembled quickly, forming massive concentrations of stars in compact regions. Others grew more gradually, building up their stellar populations through steadier star formation. Still, others likely grew through mergers, smaller proto-galaxies coming together under gravity's influence to create larger systems. The spatial distribution of these early galaxies also tells us something profound about the universe's structure. Even at these early times, galaxies weren't randomly scattered through space. They were already beginning to trace the large-scale structure, the cosmic web of filaments and voids that would become more pronounced as the universe aged. Webb's observations show that some early galaxies cluster together in groups and protoclusters, while others sit in relative isolation. One particularly remarkable discovery involved confirming the existence of galaxies at redshifts of 14 and beyond. Spectroscopic observations, which measure the precise wavelengths of light from these galaxies, confirmed that some of them truly are as distant as their colors suggested. These spectroscopic confirmations are crucial because photometric estimates, based solely on the colors and brightness of galaxies in images, can sometimes be fooled by unusual objects that mimic the appearance of very distant galaxies. The spectra of these ultra-distant galaxies revealed ultraviolet continua with prominent Lyman alpha breaks, features caused by hydrogen atoms in and around the galaxies absorbing light at specific wavelengths. Interestingly, many of these galaxies show no detected emission lines, the bright features in spectra that usually come from hot gas being ionized by young stars. The absence of emission lines could mean that these galaxies are surrounded by neutral hydrogen that absorbs the emission before it can escape. Or it could indicate that their star formation is happening in an unusual way that doesn't produce the strong emission lines we see in more recent galaxies. Perhaps most tantalizing is the detection of Lyman alpha emission in a few of these ultra-distant galaxies. Lyman alpha is light emitted by hydrogen atoms, and in the neutral, hydrogen-filled early universe, this light should be strongly absorbed. That Webb can detect Lyman alpha from some galaxies at redshift 13 suggests that these galaxies have cleared bubbles of ionized transparent gas around themselves. Regions where the intense ultraviolet radiation from the galaxy's stars has split apart nearby hydrogen atoms and made the environment transparent to light. These ionized bubbles are crucial to understanding one of the most important transitions in cosmic history, the epoch of Reionization, when the entire universe transformed from opaque to transparent. We'll explore this transformation in depth later, but for now, what matters is that Webb's detection of these early ionized regions gives us direct observational evidence of the Reionization process beginning just a few 100 million years after the Big Bang, earlier than many models predicted. The star formation rates in these early galaxies are extraordinary. Some of them are forming stars at rates tens or even hundreds of times faster than the Milky Way's current rate, and they're doing so in volumes of space much smaller than our galaxy. This creates star formation surface densities comparable to the most extreme starbursts observed in the local universe, the kind of frenzied star formation we see in galaxies undergoing violent mergers. With such intense star formation, these early galaxies were blazing furnaces, forging elements in their stellar cores and distributing them through space via stellar winds and supernova explosions. They were transforming the simple chemistry of the Big Bang into the complex mix of elements that would eventually allow planets and life to form. And they were producing copious amounts of ultraviolet radiation that would eventually ionize the hydrogen-filling intergalactic space, making the universe transparent and setting the stage for the formation of future generations of galaxies. The stellar populations in these galaxies are remarkably young, with ages ranging from 16 million to 71 million years in some cases. These aren't galaxies that have been forming stars steadily for hundreds of millions of years. They're galaxies caught in the very act of their first major star formation episodes, systems where most or all of the stars have formed recently in a dramatic burst of activity. Yet, despite their youth, some of these galaxies already contain masses of stars comparable to the small Magellanic Cloud, a small satellite galaxy of the Milky Way. They've assembled billions of solar masses of stars in what, by cosmic standards, is the blink of an eye. This rapid assembly is one of the key puzzles Webb has uncovered. How did these galaxies pull together so much gas so quickly? How did they convert that gas into stars so efficiently? What mechanisms triggered their formation, and what eventually quenched their star formation in the cases where we see older, more evolved early galaxies? Every one of these early galaxies that Webb discovers is a window into cosmic dawn. That crucial epoch when the universe transitioned from a dark, simple place filled only with neutral hydrogen and helium into a rich, complex, light-filled cosmos populated by stars and galaxies. The discoveries have come so fast and been so surprising that theoretical models are struggling to keep up. That's exactly what you want from a revolutionary new instrument. Not confirmation of what we already thought we knew, but discoveries that force us to rethink our assumptions and build new frameworks for understanding. The astronomers working with Webb's data often express a sense of awe and humility about what they're seeing. Rohan Naidu of MIT, commenting on the discoveries, noted that with Webb we're able to see farther than humans ever have before, and it looks nothing like what was predicted, which is both challenging and exciting. There's a growing recognition that our understanding of the early universe may have been incomplete in fundamental ways. Looking ahead, Webb will continue to push these observations even deeper. Future surveys are planned that will search for galaxies from less than 300 million years after the Big Bang, potentially reaching back to the era of the very first stars. The telescope's spectroscopic capabilities will allow detailed studies of the chemical compositions, star formation rates, and physical conditions in these early galaxies, building up a comprehensive picture of how the first cosmic structures formed and evolved. What's becoming clear from all of these observations is that the early universe was a place of remarkable vitality and diversity. Far from being a simple, uniform epoch, where all galaxies looked roughly the same and evolved along similar paths, cosmic dawn was a time of dramatic variation, rapid evolution, and surprising complexity. The galaxies Webb has revealed from this epoch are teaching us that the universe wasted no time in creating rich and diverse structures, that the processes of star formation and galaxy growth kicked into high gear remarkably early, and that understanding how all of this happened will require new physics, new models, and new ways of thinking about cosmic evolution. In the gentle darkness around you now, imagine looking up at a sky full of these ancient galaxies, each one a blazing furnace of newborn stars, each one transforming the pristine material of the Big Bang into the elements that would one day make possible planets, and life, and consciousness. These distant lights, seen as they were billions of years before our own world formed, represent the first chapters in the story that eventually led to this moment. To you, listening to these words, contemplating the vastness of space and time. It's a connection across cosmic epochs, a thread linking the first stars to this present instant, and Webb has made that connection visible in ways we could never before have imagined. The Hubble tension, a universe expanding too fast. Let's turn our attention now to one of the deepest mysteries in cosmology, a puzzle that Webb's observations have not solved, but rather confirmed and deepened. It's called the Hubble tension, and at its heart is a simple but profound question. How fast is the universe expanding? You might think this would be an easy question to answer. Measure the distances to galaxies. Measure how fast they're moving away from us. Plot the relationship, and you have the expansion rate. Edwin Hubble did essentially this in the 1920s and 1930s, establishing what we now call Hubble's law. The farther away a galaxy is, the faster it's receding from us, with the relationship between distance and recession speed, given by a number called the Hubble constant. But measuring cosmic distances is far from simple. The universe doesn't come with mile markers or helpful signs telling us how far away things are. Astronomers have to use indirect methods, building what they call a cosmic distance ladder, where each rung depends on the one below it, and errors at any level can propagate through all the subsequent measurements. The first rung of this ladder uses stars within our own galaxy, whose distances we can measure directly through parallax, the apparent shift in a star's position as Earth orbits the Sun. These nearby stars allow us to calibrate relationships between stars' intrinsic brightness and other observable properties. One particularly important class of stars for this purpose is the Cepheid variables, stars that pulsate with regular periods, growing brighter and dimmer in predictable cycles. Henrietta Swan Leavitt discovered in the early 1900s that Cepheid variables' pulsation periods are directly related to their intrinsic brightness. A Cepheid that pulsates slowly is intrinsically much brighter than one that pulsates quickly. This relationship, once calibrated using Cepheids close enough for parallax measurements, allows astronomers to use Cepheids as standard candles. Observe a Cepheid, measure its pulsation period, and you know its intrinsic brightness. Compare that to how bright it appears, and you can calculate how far away it is. The Hubble Space Telescope spent decades measuring Cepheids in nearby galaxies, building up a robust distance scale. These measurements allowed astronomers to calibrate other distance indicators, including Type I, a supernova, stellar explosions that can be seen across vast cosmic distances. Type 1a supernovae occur when white dwarf stars accrete enough material from companion stars to trigger runaway nuclear fusion, exploding with remarkably consistent peak brightness. This consistency makes them ideal for measuring distances to far-off galaxies, where individual stars can no longer be resolved. Using this cosmic distance ladder, a team led by Adam Russ, a Nobel laureate who shared the prize for discovering that the universe's expansion is accelerating, has been refining measurements of the Hubble constant for years. Their work with Hubble led to a value of approximately 73 kilometers per second per megaparsec, meaning that for every megaparsec, about 3.26 million light-years of distance, the recession speed increases by 73 kilometers per second. This measurement is remarkably precise, with uncertainties of less than 1%. Hubble's observations of Cepheids reached out to distances of about 130 million light-years, to galaxies like NGC 5468. The telescope observed more than 1,000 Cepheids in galaxies that hosted Type 1a supernovae, providing a robust connection between the nearby distance scale and the cosmic distance scale. But here's where things get strange. Another way to measure the Hubble constant is to use observations of the cosmic microwave background, the faint afterglow of the Big Bang. The European Space Agency's Planck satellite mapped this radiation with exquisite precision, revealing temperature fluctuations of just a few parts per 100,000. These tiny temperature variations represent density fluctuations in the early universe, the seeds from which all later structure would grow. Cosmologists can use these observations, combined with our best theoretical model of how the universe evolves, to calculate what the Hubble constant should be today. This calculation relies on the lambda CDM model, our standard cosmological model incorporating a cosmological constant, lambda, and cold dark matter, CDM. The model includes parameters describing the universe's matter and energy content, including dark matter, dark energy, ordinary matter, and radiation. When you run the calculations based on Planck's observations of the cosmic microwave background, you get a Hubble constant of approximately 67.4 kilometers per second per megaparsec. That's about 8 to 9% lower than the value measured using the cosmic distance ladder. In the world of precision cosmology, where error bars are typically 1% or less, an 8 to 9% discrepancy is enormous. It's not something that can be easily explained away. This discrepancy is the Hubble tension. The word tension in science often refers to a conflict between different measurements or observations that don't quite agree. In this case, the tension is between what we observe about the universe's current expansion rate by measuring distances to nearby galaxies and what the standard cosmological model predicts that rate should be based on observations of the universe when it was just 380,000 years old. Initially, some astronomers wondered if the discrepancy might be due to measurement errors in the distance ladder. Perhaps there were systematic problems with how Hubble was measuring Cepheids. In crowded star fields, the light from a Cepheid might blend with light from nearby stars, leading to incorrect measurements of the Cepheids' brightness. Or perhaps dust in galaxies was affecting the measurements in ways not properly accounted for. This is where Webb enters the story. With its larger mirror and infrared capabilities, Webb can see Cepheids more clearly than Hubble can. Infrared light passes through dust more easily than visible light, reducing the impact of dust on brightness measurements. Webb's superior resolution can separate Cepheids from nearby stars more cleanly, eliminating the crowding problem that might affect Hubble. Adam Rice and his team used Webb to observe Cepheids that Hubble had previously measured, essentially checking Hubble's homework. They focused on galaxies containing both Cepheids and Type 1 supernovae, observing more than 1,000 Cepheids in 5 host galaxies. The Webb observations reached out to NGC 5468, the same distant galaxy that marked the edge of Hubble's Cepheid observations. The results were both gratifying and troubling. Webb confirmed that Hubble's measurements were accurate. The two telescopes produced nearly identical distance estimates, with differences of less than 2%. The cosmic distance ladder, built on decades of Hubble observations, appears to be fundamentally sound. There's no systematic error in the Cepheid measurements large enough to explain the Hubble tension. This is good news in that it validates the tremendous work that went into building and calibrating the distance ladder. But it's also puzzling news, because it means the Hubble tension is real. The discrepancy between the locally measured expansion rate and the rate predicted from the early universe is not a measurement artifact. It represents something genuine about the universe that we don't yet understand. Rees and his colleagues summarized it eloquently. With measurement errors negated, what remains is the real and exciting possibility we have misunderstood the universe. The Hubble tension is telling us that something is missing from our cosmological model, some piece of physics that hasn't been incorporated, or some assumption that needs to be revised. What could explain this discrepancy? Several possibilities have been proposed, each with its own implications and challenges. One possibility is that dark energy, the mysterious force driving the universe's accelerating expansion, is more complex than we thought. In the standard lambda CDM model, dark energy is represented by a cosmological constant, a fixed energy density in empty space that doesn't change over time. But perhaps dark energy actually varies in strength or behavior across cosmic history, in ways our current model doesn't capture. Another possibility involves the nature of dark matter. Our cosmological models assume that dark matter consists of slow-moving, cold particles that don't interact significantly with ordinary matter or light. But perhaps dark matter has properties we haven't discovered yet, properties that would affect the universe's expansion, history in subtle but measurable ways. A third possibility is more radical. Perhaps general relativity itself, Einstein's theory of gravity that has passed every test we've thrown at it for more than a century, needs modification on cosmological scales. This seems unlikely, given how well general relativity works in describing everything from GPS satellites to black holes. But if the Hubble tension persists, and no other explanation emerges, even cherished theories may need reconsideration. Some researchers have suggested that the early universe might have evolved differently than we think. Perhaps the epoch of recombination, when electrons and protons combined to form neutral hydrogen and the universe became transparent to light, occurred at a slightly different time or temperature than our models suggest. Or perhaps there was an additional source of radiation in the early universe that we haven't accounted for. The involvement of other major observatories may help resolve the mystery. NASA's upcoming Nancy Grace Roman Space Telescope will conduct wide surveys of the universe, measuring the expansion rate using multiple different methods. The European Space Agency's Euclid mission, recently launched, is creating three-dimensional maps of the universe's structure across 10 billion years of cosmic history. These observations may reveal whether the Hubble tension persists across different measurement techniques and different distance ranges. Some recent work using Webb has suggested that the tension might be smaller than previously thought, or might even disappear, depending on which distance indicators are used. Wendy Friedman of the University of Chicago led a team that used three different types of stars: Cepheids, the tip of the red giant branch stars, and carbon-rich JAGB stars to measure distances. Their analysis, incorporating Webb's improved measurements, found values for the Hubble constant that fall between the local and early universe measurements, potentially suggesting a path toward resolving the tension. However, other analyses using Webb data continue to support the larger Hubble constant value derived from Cepheids and supernovae. The picture remains confused, with different research teams using different methods arriving at different conclusions. What's clear is that Webb's observations are providing crucial new data that's helping astronomers test their measurement methods with unprecedented rigor. The stakes in this debate are high. The Hubble constant isn't just a number. It's intimately connected to fundamental questions about the universe's age, its ultimate fate, and the physical laws that govern its evolution. A change in the Hubble constant would ripple through cosmology, requiring adjustments to how we understand the universe's history and structure. Moreover, the Hubble tension may be pointing toward new physics, phenomena, or particles or forces that we haven't discovered yet. History shows that when precise observations conflict with well-established theories, the resolution often involves discovering something genuinely new. The discrepancy between Mercury's orbit and Newtonian gravity led to general relativity. The unexpected rotation curves of galaxies led to the discovery of dark matter. Perhaps the Hubble tension will lead to the next major revolution in our understanding of the cosmos. For now, the tension remains unresolved. Webb has confirmed that our local measurements of cosmic expansion are accurate, that the universe really does appear to be expanding faster in our cosmic neighborhood than the standard model predicts it should be based on conditions in the early universe. Something is going on, something we don't yet fully grasp, and it's precisely these mysteries that drive science forward, that push us to look deeper, to question our assumptions, and to seek new understanding. As you rest now, in the comfort of this moment, consider that the universe itself may be more mysterious than we ever imagined, that the very fabric of space-time may harbor secrets we're only beginning to uncover. Webb's observations haven't solved all our questions. If anything, they've shown us how much we still have to learn, how much wonder still awaits discovery in the cosmic depths. Mapping the invisible. Dark Matter's Cosmic Web. There's something both humbling and thrilling about the realization that most of the universe is invisible to us. Not just distant and faint, but fundamentally beyond the reach of light. The matter we can see, the stars and galaxies and glowing gas clouds, represents only about 15% of the total matter in the universe. The remaining 85% consists of dark matter, a mysterious substance that doesn't emit, absorb, or reflect light, making itself known only through its gravitational effects on the visible universe. Dark matter was discovered not through direct detection but through its absence, through the gap between what we see and what must be there. In the 1930s, astronomer Fritz Zwicky studied the Coma Cluster, a large collection of galaxies, and found that the galaxies were moving far too fast to be held together by the gravity of their visible matter alone. They should have flown apart long ago. Zwicky proposed that some invisible mass, much more abundant than the visible galaxies, must be holding the cluster together through its gravitational influence. Decades later, Vera Rubin's work on galaxy rotation curves provided even more compelling evidence. When you measure how fast stars orbit around the center of a spiral galaxy, you find that stars in the outer regions are moving much faster than they should be based on the visible mass of the galaxy. According to Newtonian gravity, stars far from the galactic center should orbit more slowly, just as outer planets in our solar system orbit more slowly than inner ones. But galaxies don't behave this way. Their rotation curves stay flat or even rise slightly at large distances, indicating that there's far more mass than we can see, distributed in a vast halo extending well beyond the visible galaxy. Computer simulations of cosmic structure formation confirmed that dark matter must exist and must have played a crucial role in shaping the universe. In the early universe, before the first stars formed, ordinary matter was still hot and buffeted by radiation pressure, unable to collapse effectively under its own gravity. But dark matter, immune to radiation pressure because it doesn't interact with light, could begin clumping together immediately. These dark matter clumps created gravitational wells into which ordinary matter could fall once it cooled enough. Essentially, dark matter provided the scaffolding on which the visible universe was built. But how do you map something you can't see? The answer involves one of the most beautiful predictions of Einstein's general theory of relativity: gravitational lensing. Mass warps spacetime, and light follows the curves in spacetime. When light from a distant galaxy passes through the warped spacetime around a massive object, its path bends. If we observe a background galaxy through a foreground mass concentration, the galaxy's image gets distorted, stretched, magnified, and sometimes even multiplied into several images. By carefully measuring these distortions across large areas of sky, astronomers can map where the mass is, including the dark matter we can't see directly. The more massive a region, the more it distorts background galaxies. By analyzing thousands or millions of galaxy shapes and looking for subtle patterns in how they're stretched and distorted, scientists can create maps showing the distribution of all matter, visible and dark. The Hubble Space Telescope pioneered this technique with surveys that mapped dark matter across significant regions of sky. But Hubble's resolution and survey area were limited. Enter the James Webb Space Telescope, with its larger mirror, sharper images, and ability to see fainter, more distant galaxies that Hubble missed. In early 2026, astronomers announced that Webb had produced the most detailed map of dark matter ever created. The survey focused on an area called the cosmos field, a region of sky that has been studied intensively by multiple telescopes across many wavelengths. Webb observed this region for approximately 255 hours, an enormous investment of telescope time, detecting nearly 800,000 galaxies, many of them seen for the first time. Using sophisticated analysis techniques, the team measured how the mass in the cosmos field bends space and distorts the light from distant galaxies. The resulting map reveals dark matter distribution in unprecedented detail, showing the cosmic web, the network of filaments and nodes where galaxies cluster together, shaped primarily by the gravitational influence of dark matter. The map confirms what earlier, lower-resolution observations suggested: dark matter isn't uniformly distributed through space. Instead, it's organized into a web-like structure, with dense filaments connecting massive nodes and vast voids in between containing relatively little matter. This cosmic web is one of the largest known structures in the universe, spanning billions of light-years and defining the overall architecture of cosmic structure. The resolution of Webb's dark matter map is approximately twice as sharp as previous maps created using Hubble or ground-based telescopes. Features that appeared as blurry regions in earlier maps are now crisp and well-defined. The map includes roughly 10 times more galaxies than earlier ground-based maps of the same region, providing far more data points for measuring the lensing distortions. Dr. Diana Scognamiglio of NASA's Jet Propulsion Laboratory, one of the research leaders, described it beautifully. Previously, we were looking at a blurry picture of dark matter. Now, Webb has brought it into focus. This high-resolution view reveals new concentrations of dark matter, structures that were too faint or too small to detect in previous surveys. Some of these concentrations correspond to known galaxy clusters, confirming that visible galaxies trace the peaks in the dark matter distribution. But the map also reveals dark matter structures that don't have obvious visible counterparts, regions where dark matter has concentrated, but where, for whatever reason, galaxy formation hasn't been particularly efficient. The filaments connecting the major nodes show remarkable structure. Rather than being smooth tubes of matter, they appear knotted and clumped, with substructures on many different scales. Galaxies are strung along these filaments like beads on a cosmic string, their positions marking where gas flowing along the filaments has cooled and condensed to form stars. Between the filaments lie the voids, enormous regions containing very few galaxies and very little matter of any kind. These voids aren't completely empty. They contain some diffuse gas and the occasional small galaxy, but they represent the largest empty spaces in the universe, vast bubbles in the cosmic foam. Some cosmic voids span hundreds of millions of light-years across, so large that light takes longer to cross them than the entire history of life on Earth. The dark matter map also provides crucial information about how structure formed in the universe. By comparing the observed dark matter distribution to predictions from computer simulations, astronomers can test their models of cosmic evolution. The simulations start with the tiny density fluctuations imprinted in the cosmic microwave background, then evolve the universe forward through billions of years, tracking how dark matter collapses under gravity, how ordinary matter falls into dark matter halos, how galaxies form and merge, and how the large-scale structure emerges. Webb's observations show excellent agreement with the standard lambda-CDM cosmological model in terms of the overall structure and properties of the dark matter distribution. This agreement strengthens confidence in the model and in our understanding of how the universe evolved from a smooth, nearly uniform state to the richly structured cosmos we observe today. However, the observations also reveal some intriguing discrepancies on smaller scales. The distribution of dark matter on the scale of individual galaxy clusters shows some features that simulations don't perfectly reproduce. These differences might indicate that our models need refinement, or they might point toward new physics in how dark matter behaves or interacts. One particularly interesting aspect of the dark matter map is how it connects to the visible universe. The map shows that galaxy formation is a highly biased process. Galaxies don't form everywhere that dark matter concentrates. Instead, they tend to form in regions where dark matter halos have certain properties, like particular masses or environments. Understanding this bias, how the visible universe traces the underlying dark matter distribution, is crucial for using galaxy surveys to map the universe's structure. The map also provides insights into how galaxies acquire their gas. In the standard picture, gas flows into dark matter halos along filaments, funneling material from the cosmic web toward galaxies. Once the gas reaches the halo, it can cool and fall toward the galaxy's center, fueling star formation. Webb's dark matter map, combined with observations of gas in and around galaxies, is helping astronomers test this picture and understand how the cosmic web feeds galaxy growth. Looking at the early universe, the dark matter distribution appears somewhat different from today's. The cosmic web was denser, with filaments closer together and voids smaller and less empty. This evolution reflects the universe's expansion. As space stretches, the web stretches with it, filaments spreading apart and voids growing larger. Meanwhile, gravity continues to pull matter into filaments and nodes, making the densest regions even denser while depleting the voids further. Webb's ability to see distant galaxies allows the dark matter mapping to extend across cosmic time. By measuring lensing effects from galaxies at different distances, astronomers can create dark matter maps from different epochs in the universe's history, showing how the structure evolved from an earlier, denser configuration to the more spread-out web we see today. The dark matter maps also constrain dark matter's properties. Different dark matter models predict subtly different structures. If dark matter consists of heavy, slow-moving particles, as the standard cold dark matter model assumes, you get one pattern. If dark matter is lighter and faster, warm dark matter, you get a different pattern with less structure on small scales. If dark matter can interact with itself through some dark force, you get yet another pattern. Webb's observations are precise enough to distinguish between some of these possibilities, narrowing down what dark matter could be. Ultimately, the cosmic web of dark matter is the foundation upon which everything else rests. Galaxies formed where dark matter concentrated. Stars formed in those galaxies. Planets formed around those stars. And on at least one of those planets, life emerged and eventually evolved into beings capable of looking back across cosmic distances and mapping the invisible scaffolding that made everything possible. As you rest in this moment, comfortable and relaxed, consider that the very earth beneath you, the atoms in your body, everything you've ever seen or touched or experienced, exists only because dark matter's gravitational pull shaped the early universe in specific ways. We are, in a very real sense, products of the cosmic web, our existence tied to structures formed from invisible matter we still don't fully understand. Webb's map of this dark matter distribution is a map of our origins, a chart showing the deep architecture that underlies all of cosmic history. The Epoch of Reionization, when light conquered darkness. Imagine a universe shrouded in fog, where no light could travel more than a short distance before being absorbed. a universe where the space between stars, between galaxies, was opaque, filled with neutral hydrogen gas that greedily absorbed ultraviolet photons. This was the state of the cosmos for hundreds of millions of years after the Big Bang, during an epoch astronomers call the Dark Ages. The story of how light conquered this darkness is one of the most important chapters in cosmic history, and it's a story that the James Webb Space Telescope is revealing in unprecedented detail. Let's begin at the beginning. About 380,000 years after the Big Bang, the universe had expanded and cooled enough for electrons and protons to combine into neutral hydrogen atoms. This moment, called recombination, marks when the universe became transparent to light for the first time. Before recombination, space was filled with a hot plasma where electrons and protons bounced around freely, constantly scattering photons. Light couldn't travel far through this plasma. It was like trying to see through a thick fog. But when recombination occurred, when electrons settled into orbits around protons to form neutral atoms, the photons that had been trapped in constant scattering were suddenly free to travel unimpeded. This moment gave birth to the cosmic microwave background radiation that satellites like Planck have mapped so precisely. The universe had become transparent, and those freed photons have been traveling through space ever since, carrying information about what the universe was like at that early time. However, the transparency didn't last. The universe quickly filled with neutral hydrogen gas, and this gas, while it let the cosmic microwave background photons pass through, absorbed ultraviolet light. Any source of ultraviolet radiation, any early star trying to shine, would find its light, absorbed by the surrounding neutral hydrogen. The universe had become transparent at some wavelengths, but opaque at others. And then, for hundreds of millions of years, there were no sources of light anyway. The cosmic microwave background radiation faded to lower and lower energies as the universe expanded. The matter in the universe consisted almost entirely of neutral hydrogen and helium, the elements created in the Big Bang. This gas-filled space, slowly collapsing under gravity into denser and denser regions, guided by the distribution of dark matter. These were the Dark Ages, a time when the universe was literally dark. No stars had ignited, no galaxies had formed. Space was cold and neutral and filled only with the fading afterglow of the Big Bang. The Dark Ages ended when the first stars formed, probably somewhere between 100 million and 200 million years after the Big Bang, though the exact timing is still uncertain. These first stars, called Population 3 stars, would have been very different from the Sun and other modern stars. With no heavy elements available, since none had yet been created in stellar cores and distributed by supernova explosions, these stars formed from gas that was almost pure hydrogen and helium. Theoretical models suggest that Population 3 stars would have been massive, probably dozens or even hundreds of times the Sun's mass. Such massive stars burn hot and fast, with surface temperatures far higher than the Sun's, producing copious amounts of ultraviolet radiation. They would have lived short lives, perhaps just a few million years, ending in spectacular supernova explosions that seeded the surrounding gas with the first heavy elements. When these first stars ignited, their ultraviolet light began ionizing the hydrogen around them, splitting neutral hydrogen atoms into free protons and electrons. Around each early star, or more likely around each early galaxy containing many stars, an ionized bubble began to grow. Inside these bubbles, the gas was transparent to ultraviolet light. Outside, the universe remained neutral and opaque. This process of ionizing the neutral hydrogen filling the universe is called reionization. It's a bit of a confusing name since the hydrogen wasn't ionized before, it was neutral after recombination, but the term stuck. The epoch of reionization refers to the period when these ionized bubbles around galaxies expanded and eventually overlapped, transforming the entire universe from neutral to ionized, from opaque to transparent. The standard model of cosmology suggested that reionization began around 500 million years after the Big Bang, and completed another 500 million years later, around 1 billion years post-Big Bang. But Webb's observations are challenging this timeline, suggesting that reionization may have started earlier and progressed differently than we thought. One of Webb's most remarkable discoveries involves detecting Lyman alpha emission from galaxies at redshift 13, corresponding to just 330 million years after the Big Bang. This is significant because Lyman alpha light, emitted by hydrogen atoms, is strongly absorbed by neutral hydrogen. In a universe filled with neutral hydrogen, Lyman alpha emission shouldn't escape from galaxies. It should be absorbed by the surrounding gas before it can reach our telescopes. That Webb can detect Lyman alpha from some ultra-distant galaxies suggests that these galaxies have cleared ionized bubbles around themselves. The ultraviolet radiation from the galaxy's stars has ionized the nearby hydrogen, creating a region of transparent gas through which Lyman alpha light can escape. This detection provides direct observational evidence that reionization had begun by 330 million years after the Big Bang, earlier than many models predicted. The galaxy showing this Lyman alpha emission is particularly intriguing. Its spectrum shows a singular bright emission line unambiguously identified as Lyman alpha, as well as a smooth turnover in its ultraviolet continuum. This turnover is called a damping wing, caused by absorption of light by neutral hydrogen surrounding the galaxy's ionized bubble. The combination of detected Lyman alpha emission and the damping wing signature tells astronomers that they're seeing a galaxy surrounded by a bubble of ionized gas embedded in a larger region of neutral hydrogen. The researchers studying this galaxy believe they've discovered one of the first ionized bubbles created during reionization. Computer simulations show that these bubbles initially form around individual galaxies or small groups of galaxies, growing as the central sources continue producing ionizing radiation. Over hundreds of millions of years, the bubbles expand and eventually begin to overlap. Once enough bubbles have overlapped, the universe reaches a percolation threshold where the ionized regions connect across the entire universe, and reionization is complete. Finding a galaxy with a Lyman alpha detection at such an early epoch suggests that the bubbles were forming earlier than some models predicted. It also provides a way to probe the conditions during reionization. By studying the properties of the Lyman alpha emission, how bright it is, how the line is shaped, astronomers can learn about the size of the ionized bubble, the density of neutral hydrogen outside the bubble, and the strength of the ionizing radiation coming from the galaxy. Webb has found other galaxies from this epoch that don't show Lyman alpha emission, even though they appear to be forming stars at high rates and should be producing strong Lyman alpha radiation. These galaxies might be in regions where the surrounding neutral hydrogen is so dense that it absorbs all the Lyman alpha before it can escape, even if small ionized bubbles exist around the galaxies. Or they might be galaxies whose ionizing photons are escaping into the surrounding intergalactic medium rather than being absorbed locally to produce Lyman alpha emission. The diversity of what Webb sees, some galaxies with Lyman alpha, some without, galaxies with different spectral features and different apparent levels of metal enrichment, suggests that Reionization was not a uniform process. Different regions of the universe were being ionized at different rates, with some areas becoming transparent early, while others remained neutral for longer. This patchiness in the Reionization process is expected based on computer simulations. Ionizing radiation comes primarily from galaxies, and galaxies aren't uniformly distributed. They cluster together along the filaments of the cosmic web, with voids between the filaments containing few galaxies. Regions with many galaxies, like protoclusters, would have produced copious ionizing radiation and reionized early. Regions with few galaxies, like voids, would have taken longer to ionize, perhaps remaining neutral until ionizing photons from surrounding regions finally penetrated them. The implications of reionization extend beyond just making the universe transparent. The process of ionization pumps energy into the intergalactic medium, heating it to temperatures of tens of thousands of degrees. This heating affects how gas can cool and fall into galaxies to form stars. Before reionization, gas could cool efficiently and collapse into even small galaxies. After reionization, the heating suppresses star formation in the smallest galaxies, particularly those in the low-density voids. This differential suppression of star formation in different environments helps explain the observed distribution of galaxies today. Massive galaxies formed in high-density regions before reionization and continued growing afterward. Dwarf galaxies in high-density regions also formed early and could continue growing by accreting pre-enriched gas from their environments. But potential dwarf galaxies in voids, which might have formed late, never had the chance because reionization heated the gas and prevented it from cooling and collapsing. The metal enrichment that Webb observes in some early galaxies also ties into reionization. The first stars, those population 3 stars, contained no metals, but they created metals through nuclear fusion in their cores and distributed them through supernova explosions. The next generation of stars formed from gas enriched with these metals, and those stars produced even more metals, gradually building up the chemical complexity we see in later cosmic epochs. Galaxies with higher metal content produce more ionizing photons per unit star formation rate, because metals affect how stars form and how efficiently they convert their mass into radiation. This means that once galaxies reached a certain level of metal enrichment, they became more effective at ionizing their surroundings, potentially accelerating the reionization process. Webb's detection of nitrogen-rich galaxies at very early times is particularly intriguing in this context. Nitrogen is produced primarily in intermediate mass stars through a complex sequence of nuclear reactions. Seeing elevated nitrogen levels in galaxies just a few 100 million years after the Big Bang suggests that stellar evolution and chemical enrichment proceeded faster than expected. It might also indicate that the initial mass function, the distribution of masses for newly formed stars, was different in the early universe, favoring the intermediate mass stars that produce nitrogen. The role of supermassive black holes in reionization is another puzzle that Webb is helping to address. Many of the early galaxies Webb has detected show signs of active galactic nuclei. Supermassive black holes at their centers that are actively accreting gas and producing enormous amounts of radiation. These black holes can produce hard ultraviolet and even X-ray photons that are particularly effective at ionizing hydrogen. If supermassive black holes formed rapidly in the early universe, they could have contributed significantly to reionization. Some models suggest that black holes might have been more important than stars in ionizing the intergalactic medium, especially in the later stages of reionization. Webb's observations of black hole activity in early galaxies are providing crucial data for testing these models. The connection between reionization and galaxy formation creates a feedback loop. Galaxies produce the ionizing radiation that drives reionization. But reionization, by heating the intergalactic medium, affects how subsequent galaxies can form. Understanding this feedback loop is crucial for explaining why the universe looks the way it does today. One fascinating aspect of reionization studies is that they're probing one of the last major phase transitions in cosmic history. The universe has gone through several phase transitions. Thus, a separation of forces in the first fraction of a second after the Big Bang, the formation of protons and neutrons, the synthesis of the first atomic nuclei, the formation of the first atoms at recombination. Reionization represents the last of these major transitions, when the universe changed from a state where most hydrogen was neutral to one where most hydrogen is ionized. This transition had profound consequences for how light propagates through the universe. After reionization, ultraviolet light could travel unimpeded across cosmic distances, allowing the universe we observe today to exist. If reionization hadn't occurred, we wouldn't be able to see distant galaxies in ultraviolet light. The universe would appear fundamentally different, and the evolution of structure would have proceeded along a different path. As we've traced this journey from darkness to light, from a universe filled with neutral gas to one where ionized bubbles expanded and merged, we've been following one of the key transitions that made the modern universe possible. Webb's observations are illuminating this transition in ways we've never seen before, showing us the individual galaxies that were the first to clear bubbles of transparency in the cosmic fog, revealing how quickly and efficiently these early sources could ionize their surroundings. In the quiet of this moment, as you rest and let these ideas wash over you, consider that the light reaching your eyes right now, whether from a screen or a lamp or the stars outside, travels freely through space because of events that occurred over 13 billion years ago. The first stars and galaxies fought against the darkness, their radiation gradually transforming the universe into a place where light could flow freely. That transformation, that cosmic brightening, was one of the essential steps in the chain of events that led to our existence. And Webb has given us our first clear views of how it all unfolded. Scale beyond comprehension. To truly grasp what the James Webb Space Telescope has revealed about the universe's scale, we need to build up our sense of cosmic distances step by step, starting from something familiar and venturing outward into the incomprehensible. Let's begin with Earth, our home. Earth is about 12,742 kilometers in diameter, a sphere of rock and metal wrapped in a thin shell of water and air. This is a size we can almost grasp. You could drive around Earth's equator in a car, though it would take you weeks of continuous driving. Commercial airplanes circle the globe routinely, taking roughly 40 hours for the journey. Now, step outward to our solar system. The Sun sits at the center, a sphere of plasma about 140 times Earth's diameter. The distance from Earth to the Sun, approximately 150 million kilometers, is called an astronomical unit. Light, traveling at 300,000 kilometers per second, takes about 8 minutes and 20 seconds to cross this distance. The outermost major planet, Neptune, orbits about 30 astronomical units from the Sun, 30 times farther than Earth. Light takes about 4 hours to reach Neptune. The solar system's edge, marked by the Kuiper belt of icy objects and the distant Oort cloud of comets, extends perhaps 100,000 astronomical units from the Sun, well over a light year. Now, make the next leap to the nearest stars. Proxima Centauri, the closest star to our Sun, lies about 4.2 light-years away. If you could somehow travel at the speed of light, which physics tells us is impossible for anything with mass, it would still take you over 4 years to reach our nearest stellar neighbor. At the speed of our fastest spacecraft, it would take tens of thousands of years. The stars you see in the night sky, the familiar constellations, are almost all within a few hundred light-years of Earth. These nearby stars represent a tiny fraction of our galaxy, the Milky Way, which stretches about 100,000 light-years from edge to edge. Our Sun orbits in the Milky Way's outskirts, about 26,000 light-years from the galactic center, taking approximately 230 million years to complete one orbit. The Milky Way contains somewhere between 200 billion and 400 billion stars. If you could somehow visit a new star every second, it would take you more than 6,000 years just to visit them all once. Each of these stars potentially hosts its own system of planets, meaning our galaxy alone might contain trillions of worlds. But the Milky Way is just one galaxy among billions in the observable universe. The nearest large galaxy to ours is Andromeda, located about 2.5 million light-years away. The light you see from Andromeda tonight actually left that galaxy 2.5 million years ago, when our ancestors were just beginning to fashion crude stone, tools in Africa. In about 4 billion years, the Milky Way and Andromeda will collide and merge, creating a new, larger galaxy in a process that will take hundreds of millions of years to complete. The Milky Way and Andromeda are the 2 largest members of the local group, a collection of more than 50 galaxies bound together by gravity and spanning about 10 million light-years. To put this in perspective, it would take more than 100 Milky Way galaxies lined up end to end to span the local group's diameter. But the local group is a small structure on cosmic scales. It sits on the outskirts of the Virgo supercluster, a vast collection of galaxy groups and clusters spanning about 110 million light-years. The Virgo cluster sits near the center of this supercluster, containing thousands of galaxies in a region about 15 million light-years across. The gravitational pull of this massive cluster is actually drawing the local group and the Milky Way toward it, though we'll never complete the journey before the accelerating cosmic expansion tears the supercluster apart. Recent surveys have revealed that the Virgo supercluster is itself part of an even larger structure called the Laniakea supercluster, which spans about 520 million light-years. The name Laniakea comes from Hawaiian words meaning immense heaven, and it's an apt description for a structure containing the mass of about 100,000 trillion suns distributed among 100,000 galaxies. And Laniakea is just one of many such superclusters scattered across the observable universe. These superclusters are connected by filaments of galaxies, creating the cosmic web that Webb's dark matter observations have mapped in such detail. Between the filaments lie the voids, enormous empty regions hundreds of millions of light years across. Now we come to the edge, to the limits of the observable. The most distant objects Webb has detected lie approximately 13.5 billion light-years away in terms of light travel distance, meaning their light has been traveling toward us for 13.5 billion years. But remember, space has been expanding while that light traveled. Those galaxies are now much farther away, perhaps 30 billion light-years or more, carried to those distances by the expansion of space itself. The edge of the observable universe, the cosmic horizon beyond which we cannot see because light hasn't had time to reach us since the Big Bang, lies approximately 46.5 billion light-years away in all directions. This creates an observable sphere with a diameter of approximately 93 billion light-years. To put this in terms of Milky Ways, you would need to line up about 930 million copies of our galaxy, end to end to span the observable universe's diameter. Think about that. Our galaxy, containing hundreds of billions of stars, is such a tiny fraction of the observable universe that you'd need nearly a billion of them to measure across it. Or consider it in terms of time. If you could somehow travel at the speed of light, starting from one edge of the observable universe and heading toward the other, you would travel for 93 billion years, more than 6 times the current age of the universe. Of course, you can't actually make this journey, both because nothing can travel at light speed, and because the expansion of space means the edge is receding faster than light can chase it. The numbers become so large they lose meaning in ordinary terms. The observable universe contains roughly 2 trillion galaxies, each with hundreds of billions of stars. The total number of stars in the observable universe might exceed 1 septillion, a 1 followed by 24 zeros. If every star hosted an average of 1 planet, and you could visit a billion planets per second, it would still take you billions of years to visit them all. Yet, even this incomprehensible scale represents only what we can see, only the portion of the universe from which light has had time to reach us. The full universe, if it's infinite as many cosmologists suspect, is much, much larger than this observable portion. Beyond our cosmic horizon lie more galaxies, more stars, more worlds, continuing perhaps forever in all directions. Some regions beyond our horizon may be very similar to our own, with galaxies and stars forming through the same physical processes. Other regions might be dramatically different if the laws of physics or the values of fundamental constants vary across the full universe. We may never know, because the accelerating cosmic expansion means that light from those distant regions will never reach us. Think about what Webb has shown us within this vast arena. Those deep-field images revealing thousands of galaxies in patches of sky the size of a grain of sand at arm's length are showing us structure on scales of billions of light-years. Each galaxy in those images represents a location in space where hundreds of billions of stars have gathered under gravity's influence, where planets orbit those stars, where perhaps in some cases life has emerged and evolved. And yet, despite the overwhelming vastness, despite scales that dwarf human comprehension, there's something deeply moving about our ability to measure and map this immensity. We're tiny creatures on a small planet, orbiting an ordinary star in an unremarkable galaxy. Yet we've built instruments capable of detecting light from the edge of creation. We've developed mathematical frameworks that allow us to understand cosmic expansion, dark matter, galaxy formation. We've traced the universe's history from a hot, dense beginning through 14 billion years of evolution to the richly structured cosmos we observe today. The James Webb Space Telescope represents the culmination of this quest to understand cosmic scale. Its observations have pushed our vision farther than ever before, revealing galaxies from when the universe was just a few 100 million years old, mapping the distribution of dark matter across billions of light years, confirming and deepening mysteries like the Hubble tension, showing us the epoch of Reionization in unprecedented detail. As you rest in this moment, comfortable and still, let the scale of what Webb has revealed settle into your awareness. You exist within a universe of 93 billion light-years diameter, packed with trillions of galaxies, each galaxy containing billions or hundreds of billions of stars. That same universe was once smaller than a single atom, expanded to its current vast size, and is still expanding, carrying galaxies apart at speeds that increase with distance until, at the cosmic horizon, space itself recedes faster than light. You are connected to all of this through an unbroken chain of cause and effect, stretching back to the Big Bang. The atoms in your body were forged in stellar cores and scattered by supernova explosions billions of years ago. The oxygen you breathe, the carbon in your cells, the calcium in your bones, all of it was created in stars that lived and died before our sun even formed. You are, quite literally, made of stardust, a small part of the universe that has become conscious and is now contemplating its own vastness. Webb's revelation of cosmic scale is ultimately a revelation about our place within that scale. We're infinitesimal compared to the universe's vast extent, yet we're capable of comprehending it, of building tools to observe it, of asking questions about its origin and fate. That capacity, that spark of understanding in the cosmic immensity, is perhaps the most remarkable thing of all, the future of discovery. The James Webb Space Telescope has been operating for less than 3 years as of this writing in early 2026, yet it has already transformed our understanding of the cosmos. The discoveries we've explored, the earliest galaxies, the detailed dark matter maps, the confirmation of the Hubble tension, the glimpses of Reionization, these are just the beginning. Webb has decades of observations ahead of it, potentially, and each year will bring new revelations, new puzzles, new wonders. The telescope's scientific program continues to expand. The fifth cycle of observations, beginning in 2026, received a record-breaking 2,900 proposals from astronomers around the world, all eager to use Webb's capabilities to explore their favorite corners of the cosmos. These proposals span everything from studying planets in our own solar system to searching for the most distant galaxies, from mapping star formation in nearby nebulae to investigating the properties of dark energy. One particularly exciting area for future observation involves the detailed study of exoplanet atmospheres. Webb has already detected water vapor, carbon dioxide, and other molecules in the atmospheres of planets orbiting other stars. Future observations will extend this work to smaller, more Earth-like planets, potentially detecting biosignatures, gases like oxygen and methane that might indicate the presence of life. The search for population 3 stars, those first stars formed from primordial gas containing no heavy elements, continues. Webb has pushed back to galaxies formed just a few 100 million years after the Big Bang. But the very first stars might have formed even earlier, perhaps 100 million years post-Big Bang or less. Detecting these first stars, or at least the galaxies they formed in, remains one of Webb's primary goals. understanding the nature of dark matter and dark energy is another key objective. While Webb can't detect dark matter directly, its observations of how dark matter shapes galaxy formation and evolution, combined with its mapping of the cosmic web, provide crucial constraints on dark matter's properties. Similarly, Webb's observations of distant supernovae and the large-scale structure help refine our understanding of dark energy, the mysterious force driving cosmic acceleration. The Hubble tension remains unresolved, and Webb's continued observations will play a crucial role in either solving this mystery or deepening it. Future measurements using improved techniques and larger samples of distance indicators will further test whether the discrepancy is real and what its implications might be for fundamental physics. But Webb won't work alone. Other major observatories will complement and extend its observations. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2000s, will conduct wide-field surveys that will discover thousands of exoplanets through gravitational microlensing and map the distribution of dark matter and dark energy across large swaths of sky. Roman's combination of wide field of view and deep sensitivity will provide a complementary perspective to Webb's focused, deep observations. The European Space Agency's Euclid mission, launched in 2023, is already creating three-dimensional maps of the universe's structure across 10 billion years of cosmic history. Euclid's observations of billions of galaxies will help trace how dark matter and dark energy have influenced cosmic evolution, potentially helping resolve mysteries like the Hubble tension. Ground-based observatories continue to push boundaries as well. The extremely large telescope, currently under construction in Chile, will have a mirror 39 meters in diameter, making it the largest optical/infrared telescope ever built. When it begins operations in the early 2030s, it will be able to study the atmospheres of Earth-like exoplanets and image details in distant galaxies that even Webb cannot resolve. The Vera C. Rubin Observatory, also in Chile, will conduct the legacy survey of space and time, photographing the entire visible sky every few nights for 10 years. This survey will discover millions of transient events, asteroids, variable stars, and distant galaxies, creating a time-lapse movie of the universe's evolution. Looking farther ahead, concepts exist for even more ambitious space telescopes. The Habitable Worlds Observatory, a proposed flagship mission that would succeed Webb, would focus specifically on finding and characterizing potentially habitable exoplanets. With a mirror potentially larger than Webb's and instruments designed for extreme stability and contrast, it could detect Earth-like planets around nearby stars and search for signs of life. Other concepts include interferometers in space, multiple telescopes flying in formation to create an effective aperture hundreds or thousands of meters across, far larger than any single telescope could be. Such instruments could resolve features on the surfaces of nearby planets or peer even deeper into the early universe than Webb can manage. On the ground, proposals exist for telescopes with mirrors 100 meters in diameter or more. These enormous instruments would be sensitive enough to study individual stars in distant galaxies, trace the chemical evolution of galaxies across cosmic time, and potentially detect atmospheres around rocky planets in the nearest star systems. The next few decades promise to be extraordinary for astronomy and cosmology. The combination of Webb's deep observations, Roman's wide surveys, Euclid's three-dimensional mapping, ground-based extremely large telescopes, and potentially new space-based observatories will provide an unprecedented multi-wavelength, multi-scale view of the universe. we'll likely find the answers to many current questions. How common are Earth-like planets around other stars? Are we alone in the universe, or has life emerged elsewhere? What is dark matter made of? What is dark energy, and will it drive the universe's expansion forever? How did the first stars and galaxies form? Can we detect the signatures of population 3 stars? What is the true value of the Hubble constant? And what is causing the Hubble tension? But history suggests that for every question we answer, we'll discover several new mysteries. The universe has a way of surprising us, of revealing complexities we hadn't imagined. Webb's discovery of unexpectedly bright and mature galaxies in the early universe is just the latest example. Before Webb, we thought we understood early galaxy formation reasonably well. Now we know we're missing something fundamental. This is the nature of scientific progress. Each generation of telescopes extends our vision farther and reveals new phenomena that challenge our theories. The questions we'll be asking in 20 or 30 years, based on observations from Webb and its successors, might be questions we can't even formulate yet because we don't know what we don't know. What's certain is that the quest to understand the universe, to map its scale, to trace its history, to comprehend the physical laws that govern it, will continue. The James Webb Space Telescope is a milestone in this quest, a powerful tool that has dramatically extended the frontier of human knowledge. But it's not the end of the journey. It's a step, an important step, but still just one step in an ongoing exploration that may have no final destination. As you drift now, relaxed and peaceful, consider that you're living through a golden age of astronomical discovery. The observations being made right now by Webb and other instruments are revealing truths about the cosmos that humans have wondered about for millennia. The scale of the universe, the nature of its contents, the story of its evolution from a hot, dense beginning to the vast, structured cosmos we observe today. All of this is being illuminated in unprecedented detail. Future generations will look back at this era as the time when we first really saw the early universe, when we mapped the cosmic web in detail, when we began to seriously search for life on other worlds. They'll study the discoveries being made now in the same way we study the work of Galileo, of Hubble, of Einstein. And they'll push beyond, using tools we can barely imagine, discovering things that would astonish us. The exploration of the cosmos is an endless frontier. Each discovery opens new questions. Each answer reveals new mysteries. The James Webb Space Telescope has shown us that the universe is larger, more complex, and more wonderful than we knew. And that revelation, far from being the end of the story, is really just the beginning of new chapters yet to be written. Conclusion. As we near the end of our journey together through the cosmic revelations of the James Webb Space Telescope, let yourself settle even deeper into comfort. Feel the gentle pull of relaxation drawing you toward rest, like gravity drawing gas into the first galaxies in the early universe, inevitable and natural. We've traveled together across distances that dwarf imagination, from the familiar confines of Earth to the edge of the observable universe 93 billion light-years away. We've looked back through time to see galaxies as they existed just a few 100 million years after the Big Bang, witnessing the cosmic dawn when the first stars ignited and the first structures assembled from primordial gas. We've traced the invisible architecture of dark matter, the scaffolding on which everything visible is built. We've explored the mysteries of cosmic expansion, the Hubble tension reminding us that the universe still holds secrets we haven't unraveled. What the James? Webb Space Telescope has revealed is that the true scale of the universe extends far beyond simple measurements of distance. Yes, the observable universe stretches 93 billion light-years across. Yes, it contains perhaps 2 trillion galaxies. Yes, the numbers are almost incomprehensibly large. But the deeper truth is about the richness of structure, the complexity of cosmic evolution, the interconnectedness of everything that exists. You are part of this cosmic story. The atoms in your body were forged in stars billions of years ago. The oxygen you breathe was created when massive stars fused lighter elements in their cores and then exploded, scattering those elements through space. The calcium in your bones, the iron in your blood, the carbon that forms the basis of all your body's molecules, all of it came from stellar alchemy, from processes occurring in stellar cores where temperatures and pressures are so extreme that they transform one element into another. In a very real sense, you are the universe looking at itself, a small part of the cosmos that has become conscious and is now contemplating the whole. This capacity for understanding, for building instruments like Webb that can peer back nearly to the moment of creation, for asking questions about where we came from and what it all means. This is perhaps the most remarkable thing in a universe full of wonders. As you rest now, in this moment of peace and stillness, you're connected to everything we've discussed. The same gravitational force that shaped the cosmic web also holds you gently to Earth's surface. The same electromagnetic force that allows electrons to bind to atomic nuclei, creating the neutral atoms from which everything is built, also carries the signals in your nervous system and allows light to travel from distant galaxies to Webb's mirror and sensors. The scale that Webb has revealed, that 93 billion light-year sphere of space packed with structure and history, is humbling. We're infinitesimal compared to the cosmos's vast extent. Our lives are brief flickering compared to the billions of years of cosmic evolution. Our planet is a tiny mote of dust orbiting an ordinary star in an unremarkable galaxy. And yet, somehow, against all odds, we exist. We're here, conscious and aware, capable of wonder and curiosity and understanding. We've built tools that allow us to see nearly to the edge of creation. We've developed theories that explain how the universe evolved from a hot, dense beginning to its current state. We've traced our own origins back through stellar evolution, galactic formation, all the way to the quantum fluctuations in the first moments after the Big Bang. This is the ultimate revelation of scale that Webb has given us. Not just the physical scale measured in light years and galaxies, but the scale of possibility, the profound fact that the universe is capable of producing beings who can understand it. From simple beginnings, from just hydrogen and helium and dark matter, distributed slightly unevenly in space, the universe has evolved over billions of years to create galaxies and stars and planets and, eventually, life and intelligence. As you drift toward sleep now, or simply rest in this moment of calm, let yourself feel both the vastness and the intimacy of it all. The universe is almost unimaginably large, but you're part of it, made from it, connected to it in every way. The same laws of physics that govern the expansion of space and the formation of galaxies also govern the beating of your heart and the firing of neurons in your brain. The James Webb Space Telescope has given us a gift, a new perspective on the cosmos and our place within it. It's shown us that the universe is larger and more complex than we knew, that the early universe was stranger than we expected, that mysteries remain to be solved. But perhaps most importantly, It's shown us that the quest to understand, the drive to explore and discover and comprehend is one of the most profound aspects of what it means to be human. So rest now, peacefully, knowing that you exist within a universe of extraordinary scale and beauty. The light from distant galaxies, emitted billions of years ago, is reaching Earth even now, carrying messages from the early universe. The cosmic web of dark matter continues to shape the distribution of galaxies across space. Stars are being born in nebulae throughout the cosmos, planets are forming around those stars, and the grand story of cosmic evolution continues to unfold. You're part of that story. You're made of stardust, organized into a form capable of contemplating stars. And in this moment, as you relax and let go, as you allow yourself to drift into rest or sleep, you're connected to everything that is, everything that was, and everything that will be. Thank you for joining me on this journey through the cosmos, through the discoveries of the James Webb Space Telescope, through the true scale of the universe. If this exploration has brought you peace, comfort, or wonder, I encourage you to subscribe to The Science Pillow and share these journeys with others who might find solace in the contemplation of cosmic mysteries. Every subscription, every like, helps ensure that more of these calming explorations can be created, that more people can find this peaceful corner where science and serenity meet. The universe is vast beyond comprehension, but it's also beautiful beyond description. May you carry that beauty and that vastness with you as you rest, as you dream, as you continue your own small but significant journey through space and time. The cosmos is older than we can imagine, larger than we can visualize, and stranger than we often suppose. But it's also, in a profound way, home. Sleep well, rest deeply, and know that the stars will be there when you wake, still shining, still holding their secrets, still inviting us to wonder and explore. The true scale of the universe, as revealed by James Webb, is not just a measurement. It's an invitation to awe, to humility, to appreciation for the magnificent cosmos we inhabit. Good night, and may your dreams be filled with starlight.